Swayam Prabha. Digital India. Educated India.
Hello everybody, I welcome you to the second class of our course High Performance Computing for Scientists and Engineers, and we are discussing the first module, which is Fundamentals of Parallel Computing. As the name suggests, this high performance computing is a technology which is being often deployed by people who are working in different backgrounds of science and engineering and other application areas. So this group of researchers or engineers or application people, they often do lack of a background in computer science. However, we understand that high performance computing is something which is of course one level complicated than simple computing or using a single computer, using your own desktop, or even using a very high end personal computing system. And it is usually multiple processors or multiple computers connected together which need to communicate across themselves, which need to be deployed to solve a problem in using a synchronization among themselves. So the high performance computing infrastructure typically require certain amount of understanding of computer architecture and computer science, some computer science basics. But we understand that the people who will utilize this high performance computing infrastructure are people without computer science basics. Therefore, while discussing high performance computing, especially while discussing different algorithms in high performance computing and seeing that how a simple program which is supposed to be done on a single PC can be further developed into a high performance computing program or a parallel program, it is important that we also appreciate some of the basics of the fundamentals of parallel computing infrastructure, including its architecture, including its hardware, and including the software which gives the foundation of parallel computing. It is also important that we appreciate that what is the performance of a parallel computing system which we are using, combining all the hardware, software and other backend issues. And we also understand that how when we develop a parallel computing program, when we write an algorithm which is supposed to work in a parallel computing architecture, is it utilizing all the benefits of the system that again includes the hardware and the backend softwares? Is it including all the benefits of that? Even if I am an application engineer but I am not quite sure about these basics, I might end up doing things wrong and my application can be hampered. So it is important that we understand some of the basics of parallel compute, some of the basics or fundamentals of parallel computing, including both hardware and backend softwares, some of the basics on algorithms for parallel computing, some of the basics on the architecture also. But again, while saying so, we understand that it is the job of the computer science background scientists and engineers to provide support for high performance computing and to come up with new developments in the area of high performance computing, which can be utilized by the people who are coming from the application side. So people with computer science background, they also need to understand that what is the performance of scientists and engineers working in HPC or high performance computing. So it's important to have a bridge between them, and therefore as we have developed in this course also, for people with computer science background and for people without CS background, it is important to revisit some of the basics of parallel computing. And that is why we are discussing this particular module, fundamentals of parallel computing, and we cannot avoid having some discussions on the architecture of parallel computing. Again, while saying so, I must acknowledge the fact that computer architecture is a very vast subject. It is at least a semester long undergraduate course in computer science and engineering, and it has many developments and it can go to much higher level. However, we have picked up only those areas which are absolutely essential in order to understand parallel computing. So, our focus is to learn high performance computing from an application scientist or application engineer's perspective. When we have this job set up, what are the basics we do need? And in order to learn that basics, we need to revisit or we need to revise some of the basics of parallel computing, including its architecture, including the memory models, including the programming models, including some of the parallel algorithms, and including some performance issues. So, our focus is to learn high performance computing from an application point of view. Therefore, the at least 3/4 part of this syllabus of this course will be spent on learning programming using different high performance computing infrastructure, shared memory, distributed memory, GPU. So, learning OpenMP, learning MPI, and learning CUDA programming. Again, as these programs will run on a high performance computing infrastructure, we need to learn about the architectures of high performance computing infrastructure, and we are starting that discussion. So, in this particular set of discussions, so in today's class and the subsequent classes, we will learn about architecture for parallel computing, and these are the topics we will go through it. We will first focus on architecture of a sequential computer. Then we will see what is an interconnect networks, because we understand that if multiple processors are working together, it is required that they communicate in between them. It is required that they do their jobs with a synchronized manner. It might be often desired that one processor sends some data to another processor and another receives it, which will be done through an interconnect network switch, or basically network switch which connects multiple processors. So, we will learn about the networks then. Then we will see three important components of HPC infrastructure. One is processor array, another is multiprocessor and multi-computers. Again, we will focus more on multiprocessors and multi-computers, because when we do an application using HPC in today's world, we are either using multiprocessors or using multi-computers. And then we will see the large HPC platforms, which are HPC clusters. We will also quickly see what is in a GPU or graphics processing unit, and when we will do CUDA programming later, we will see GPUs in much detail. We will look into communication costs, which is extremely vital in understanding high performance computing, because as I said, high performance computing means multiple computers or multiple processors some way connected, working together to solve different parts of the same problem. While doing that, they need to communicate across themselves, they need to do synchronization, they need to send data from one processor to another processor, or they need to write data to a common global memory space, which requires certain amount of computation and communication among themselves, which has a time delay, which has some cost in terms of computing. So, we will see what is communication cost for an HPC program, and what are the different components of the communication cost. And again, when we are running our own HPC parallel program, when we are solving a large problem in an HPC system, even if the program is developed by somebody else, we should be very careful about the communication cost, because this was when we are running the sequential program, or when we are running program in a simple PC, this cost was not there. It is a single computer which is solving the problem in communication with the memory. So, it did not have any communication cost, but when we are running many computers together in parallel to solve the same problem, We are introducing this cost which was not there earlier. Therefore, it is also important that we keep a check on the communication cost. We need to look into it in detail. And then Professor Flynn long back has specified certain taxonomy to classify different architecture of parallel computers. We will go through this Flynn's taxonomy. You will see that they are very much valid even in today's world. Well, so first we look into architecture of sequential computer. When we say sequential computer, it is a simple computer that we discuss. It has a single CPU and a single memory unit. Sequential means give any job, it will process the given set of instructions, it will process the instructions in a sequential manner one by one. There is no parallel processing of the information of the instruction. You give an instruction, it will process it, that next instruction will be followed up only once the first instruction is finished. So even when we talk about sequential computer, we are not discussing about today's multi-core computer, we are discussing about a computer which has one CPU inside which there is one arithmetic logical unit which is connected with a register and a control unit. So these registers, they take small amount of memories and ask the arithmetic logical unit to work on these memories and give the output. And this sequential computer CPU takes data from a dynamic random access memory or DRAM. So when you go to buy a CPU, when we go to buy a computer, we look for the CPU's in terms of CPU speed, that what is the how many gigahertz processing cycles that CPU will give, and what is the size of this dynamic RAM and what is its speed. These two things we look into. So when and then this connection, the CPU memory arrangement, this is what is in the motherboard of the computer. This is connected through an IO or input output controller to input output devices. They are the hard disk drives, the mouse, keyboard, monitor, etc., network modem, and if it is in an embedded system, it is connected through instrumentation to robots or to some of the actuators or sensors which are working. Now when this is working, there is an instruction stream which follows the input device basically launches the program into through the control unit, and an instruction stream goes to CPU. It takes some data from the memory and processes from the main memory RAM and processes the instruction here. These two streams of process are important. One is the data stream, the data is fetched from memory, goes to the CPU and CPU returns the data back. Another is instruction stream, that this set of instructions are given to the CPU, it processes those instructions on the memory on the data stream, on the data that it has fetched from the memory. So if we look into the performance of the sequential computer, there are two performance metrics. One is the processor speed. As I said, when we go to market and try to buy a computer, we look into the processor speed, that how many gigahertz is the speed of the processor. And if we say 1 gigahertz processor, that means one cycle of electric pulse through this processor takes 10 to the power minus 9 seconds. So in 1 second there are 10 to the power 9 cycles. If we assume that in one cycle of electricity through the processor, there are 4 floating point operations done. Floating point operations means you simply take numbers, do something with the number, plus, minus, addition, division, multiplication, some operation with the number, that is a floating point operation. It is done again using the logical gates present in the CPU. And therefore, if there are 4 operations in one cycle, the 1 gigahertz processor typically does 10 to the power 9 cycles in 1 second, 10 to the power 9 cycles in 1 second. So if there are 4 operations, 4 floating point operations in 1 cycle, then in 1 second it will do 4 into 10 to the power 9 operations. 4 into 10 to the power 9 floating point operations are 4 gigaflops. The speed is called gigaflops. Flops is the one of the performance metrics here, which is flops means floating point operation per second. In 1 second it will do floating point. It will do operation on 10 to the 4 into 10 to the power 9 floats. The speed is 4 gigaflops. Well, we actually do not get that high speed in a normal sequential computer, and we will see why. So, if we talk about RAM, there are two important performance metrics in a RAM. One is the RAM bandwidth. That means when the CPU control unit fetches data from the RAM at one cycle, again it does that in cycle. It gives one set of instruction to the stream, it gives one set of instruction to the data stream, and one packet of data comes here. And how much data is fetched in one cycle? So it is given as how many bytes or how many words are fetched in each cycle. That is the bandwidth. And the next important thing is latency, time taken by the memory to get the instruction from processor and return data from it. So memory gets the instruction from the processor that it needs certain amount of data, memory returns the data to the processor, and this is done through the connectors, PCI bus, etc. How much time is required for that? That time is called latency. Why is it called latency? Because when processor has asked for certain data, it goes into latent state till this data is obtained from the RAM, and that is why it is called latency, because this is a time in which processor is actually not waiting, it's in the latent state and waiting for the time of for the data from the RAM. And now when again we go to buy a RAM, we look about the RAM speed, how many RPMs RAM, etc. So this latency is somewhere related with the RAM speed. Looking into the RAM speed, we can estimate that what should be the latency in the RAM. In many cases, there are other factors also. So if RAM latency is high, it will hinder the performance. That means the processor has to sit idle, though the processor can perform large number of operations in a second. But if the RAM introduces some latency, that time the processor cannot perform the operation. It is waiting for the data. Say I ask the processor to do A is equal to B plus C. So it will ask from the RAM what are the values of B and C. The RAM will send these values, it will add the values and return the value A to the RAM. So taking the values B and C and returning the value A, this will take certain amount of time. During that time the processor cannot do anything else, it has not finished A is equal to B plus C. So it is sitting idle. So if this time is high, if RAM latency is high, performance will be degraded. So we can see a small example problem. A 1 gigahertz processor with 4 operations in a cycle is connected with a RAM, and the dynamic RAM DRAM has a latency of 100 nanoseconds. So once in processor asks for some data, the RAM will take 100 nanosecond time to send the data to the processor. Now the processor ideally, because it is 1 gigahertz and does 4 floating point operations in one cycle, and there are 1 gigahertz means there are 1 gigacycles in a second, ideally it should give 4 gigaflop speed. We have seen it in last slide. Now for every operation, so ideally there will be 4 into 10 to the power 9 floating point operations in 1 second. But for every operation, the request for data from the DRAM and the data fetching, it will take 100 nanosecond. So one operation cannot be done unless this 100 nanosecond time is over. Therefore, once one operation is done, the processor has to wait for 100 nanosecond and it will get the data and finish the next operation. So though it can do 4 gigaflops operation, flop operation in a second, for every operation it has to wait for 100 nanosecond. Therefore, in 1 second it can do only 1 by 100 nanosecond operation, because it is once one operation is done, it is waiting for 100 nanosecond to get the data. Once one instruction set is launched, it is waiting 100 nanosecond to get the data. So the frequency of each operation is 1 by 100 nanosecond. In 1 second it can do only 10 into 10 to the power 6 or 10 megaflops operation. Therefore, from 4 gigaflop speed, which is the theoretical speed considering no RAM latency. RAM latency reduces the speed to 10 megaflops, much smaller, by few hundred times. Now again 10 megaflops, as we do not get 4 gigaflop speed in a normal CPU, we also do not get a slow speed as 10 megaflops. We get a speed in between them. We get a frequency in between 4 gigaflops to 10 megaflops. How is this done? This is done by using something called cache. To improve the performance, cache is used. Caches are low latency, high bandwidth memory units. These caches are placed in between processors and RAMs. So with some of the intuitions by the compiler and the programmer and the hardware itself, some memory from the RAM is already brought by the cache and sits very close to the CPU. So if CPU asks for some data, it does not need to go to the DRAM for that data, it can take this data from the cache. Caches are low latency, high bandwidth, small memory units, not the entire matrix will fit in the cache, some parts, some rows or some elements in the row of the matrix will fit in the cache. And when the CPU wants the memory, it does not need to every time go to DRAM, but it can take the memory from the cache. And they have low latency, they have high bandwidth, therefore they improve the performance of the system. Improved bandwidth and low latency in cache augments the performance, and caches are extremely important in order to estimate the performance of a computer. So if we look into a sequential computer architecture, it is not a processor memory arrangement, rather it is a processor cache memory arrangement. So there is a CPU controller register. This register has a very small memory. Any variable from cache is or DRAM is directly loaded to register, and CPU can only work on the registered variables. The size of the memory is 1 kilobyte, which is very small, and latency is very small also, it is 300 picoseconds. Now we have different layers of the cache. The fastest cache is L1 cache, which is small, 64 kilobyte, has a latency of 1 nanoseconds, and then L2 cache, L3 cache, and then the main memory, which is gigabyte. In today's world we get terabytes of memory, but the latency is high, 100 nanoseconds. When any data is used, the subsequent items are pulled into cache, and cache has latency typically of the order of the processor cycle time. So if we need to use any data from for computing, first the data comes from the RAM, and the subsequent items, if we are using an array, the subsequent items in that address space are pulled into the cache, and therefore when the CPU is working, usually it works in a loop or following some algorithm. Compiler also understands that what are the next elements that will be used for the calculation, and it brings down these elements to the cache. So when the CPU is working, it does not need to wait for 100 nanoseconds to get the, it does not need to wait for 100 nanoseconds to get the data from the DRAM, rather it only in 1 nanosecond latency it can get data from cache, and by that it can improve the performance. There can be multiple levels of cache. The amount of data pulled in cache for one DRAM access is known as cache hit ratio. So if one access to RAM is required by the CPU, how much data is already in the cache, and this is called the cache hit ratio. So for one particular data requirement from the CPU, how many times or for one certain amount of data required by the CPU, how many of this data is residing in the cache determines the cache hit ratio. If the cache hit ratio is high, that means most of the data are already in cache, which is reserved by the CPU, the performance will be good. If the cache hit ratio is poor, the performance will be bad. High cache hit ratio gives better performance. I can give you one small example. If you look into Fortran and C programs, so once any matrix is stored in C, it stores the matrix row wise. Again, once a matrix is stored in a Fortran program, the matrix in the RAM is stored column wise. So, if you are trying to access the matrix row wise, if you are using C program, row wise the data is pulled into the cache. So, next elements in the same row, the next elements in the same row are already residing in the cache. So, C program, if you are trying to access the data row wise, has a very good cache hit ratio. But if you are trying to access the data across row wise in a Fortran program, the data is in the RAM, the data is actually column wise, therefore cache has the next elements in the column, not in the row. There will be cache miss. It looks for the data, it will not find the data in the cache, it has to go to RAM. Therefore, cache hit ratio will be small and the program performance will be poorer. So, in Fortran, if you are trying to access some data, if you are using a column wise data access through your program, you will get better cache hit ratio and the performance will be good. Now, we come to multiple computer system. So, how multiple processors can be connected, and there are two typical arrangements. One is called a shared medium, that there is a single bus in which many processors are connected. There is a single bus in which memories it is connected to the main memory and other parts in the motherboard, and many processors are connected there. And the other one is that different processors are there and they are connected via an interconnect switch. So, first one is called a shared medium, the second one is called the switch interconnection medium. Interconnection network allows point to point communication across the processors. So, if we see here, this processor can address some data, this processor can address some part of the data, but they cannot privately communicate across themselves. So, they have to be anyway connected to the shared common address space. But if we see here, the processors can point to point communicate, can in private communicate. If this processor communicates with this processor, the other two processors can do that without changing anything common between them. It is a more flexible way of communicating across the processors. Also, we can put many processors together if using switch. In an shared medium, we can understand that it is a common bus in which many CPUs are connected, and there is a space issue, there are heat generation issues, there are electricity supply issue, etc. We cannot really use large number of processors in a shared medium. And while saying large number of processors, we think about really very large number of processors in a very efficient and leading HPC system. I have shown you in our first class discussion that there can be 100,000 computers which are connected together. Interconnection networks allows point to point communication. The advantage is that multiple messages can be shared across different parts of the processor, and the system can be scaled to a large number of processors, as we have told you. The disadvantage is that there will be more latency, because the communication earlier was through a common shared medium, but now the communication is through a switch, and this, as we are discussing about the communication across CPU and RAM, there is a latency. Now there is a network switch which has more latency. There will be more wait time for the CPUs to get the data. So, communication time will increase and communication overhead will increase. Shared memory machines, we should not confuse with shared memory machines. This interconnector may be used in shared memory machines also, but distributed memory machines always come up with the interconnectors. So, you should also look into shared memory or shared address space machines, that there is one interconnect network which is connected with many CPUs, and this can be through an interconnect network, this can be through a shared address connector also, and memories are connected with the interconnect network. So, these memories, though they are different pieces, they can be assumed to virtually a contiguous piece of memory, and the same memory is uniformly be accessible by all the processors which are connected to interconnect network. This is called an uniform memory access, or UMA machine, and if the processors have cache, this is called a cached uniform memory access. There is a difficulty if the processors have cache. This processor fetch some data from here the data is already residing in the cache and works on that. However, same data is already residing in the cache of the next processor, it has updated it. So, this has a non-updated value of the cached data, and there is a conflict between them. We will look into these conflicts in detail later. Same memory can be updated by multiple processors caches, which is a significant issue here. This will degrade the performance, and in order to avoid that, we need to use some cache coherent protocol. There can be false sharing, though that particular memory is not being used by the other processor. However, they are using the same cache line, and they are thinking that it is probably the same memory they are going to use, and there will be contention in between them, which is called false sharing. We will again discuss false sharing in much detail. And to avoid that, we need cache coherent system, that once memory is updated, cache is also updated. So, one processor updates something in the cache, it goes to the main memory and it is communicated to all other processors. Till then, none of the processors can do anything else. Or Snoopy cache, that the relevant locations of the cache which is being updated are utilized. So, these protocols are required for cached shared memory system, and in general shared memory systems in today's world are cached shared memory system. So, cache coherency is an important aspect in shared memory systems. The access pattern is typically called uniform memory access, UMA. There can be non-uniform memory access also. That means uniform memory access means same memory is visible uniformly by all the processors. So, we look into distributed memory platforms or message passing based platforms. There is an interconnect network, and many processors with their own caches and own memories are connected to the same interconnection networks, and these processors can communicate across themselves independently through the interconnection network. It is not a same memory which is visible to all the computers. Each processor has its own local distributed sense of memory. Therefore, it is also different memory elements and different caches given to all the processors. We do not need to think about cache coherence, false sharing, etc. Instead of using same address space, each computer has its own address space. Virtually, it can share some of its data to other computer independently through interconnect networks. So, if some of the data of this processor has to be given to the third processor, this should go through the interconnect network independently, and it is not interfering any memory of any other processor, but though it actually happens through the interconnection switches. And this is most popular and most widely used protocol for this is given through MPI or message passing interface calls. This is done through message passing interface. So, no situation like false sharing or cache coherence are there, but as all the processors have different memory and substantial amount of data from one processor to another processor has to be moved through the interconnection network, there can be large communication overhead. In our next discussion, we will look these things into detail, and we will try to understand what is communication overhead and what are the challenges it is posing to a parallel computing application. Okay, thanks.